I was at the...
I make the announcement now and maybe...
Yeah, in this couple, take it as long as possible.
Okay, good morning. Good morning, everybody. Before we start the session, I'd like to make an announcement. I've been asked to remind you that if you are going to dinner today, you need to take your batch, your dinner batch. You have two batches, one for the conference, one for the dinner, so you need to take it there. So, in order to get into dinner. So that's all I wanted to say. So now we can start with the session.
Yeah, I guess we can start. Good morning, everybody, to the fourth day of this Graphene Week. My name is Laura Chammaruki. I work at ICFO, the Photonic Institute of Barcelona, Spain, well, here. So, as a first speaker, I'm very glad to introduce Professor Clare Gray. She works at the University of Cambridge as just as less of a tenth as what her curriculum says. She specializes in applications of nuclear magnetic resonance, and it's used to study lithium-ion batteries really as a fraction of her experience research. And this morning she will talk us about applications of graphene and 2D carbons in energy storage. So please let me help welcome Dr. Gray.
Well, thank you very much. It's a delight to be here in such a large stage to tell you a little bit about what we've been doing in the last few years. Is it possible to turn the echo down? Well, anyway. The last few years to characterize a whole series of graphene-related materials and particularly different carbons for energy applications from batteries to supercapacitors. And since it's a plenary talk, I wanted to spend a little bit of time explaining why batteries are important in this space, what new research is in this area, and then tell you about how we've developed new characterization approaches to look at a variety of different materials from supercaps, hard carbons, lithium-air, and passivating layers on batteries. So I don't need to tell this audience why we're working on this area, but I just wanted to stress two applications. So we move from batteries that were developed for portable electronics, be your laptop or your mobile phone, where the batteries, though sometimes frustrating when they finish too quickly or they die within a couple of years, are essentially fit for purpose. But we now need to retool those batteries and scale them up, both for electrification of transport and storage in the grid. And we've got significant challenges in getting cheaper, safer, and batteries that last longer. So a battery that lasts longer inherently becomes more cheaper. And we have to do this in a sustainable way so that we don't increase the number of batteries that end up in landfills, and we don't have too much of a toll on environmental resources, particularly the cobalt that sits in a lot of these electric vehicles and mobile phone batteries. So storage on the grid is another critical area, and I think one has to appreciate that you can't continue to use intermittent sources of energy, be they wind or solar, and this is particularly relevant in Spain, that is one of the most advanced countries in Europe in this respect. But if you don't have a mechanism of storage, then you can't push the use of renewables to more than about 10 to 12%. And surprisingly, despite the cost, batteries already play a role in short-term applications, from frequency regulation to short-term backup, because they're able to switch on a lot more quickly than many devices. And even supercapacitors, because they're that much faster, have a role to play in this area. But we have a long way to go, and in 2014, only 0.4% of the current grid storage comes from electrochemical devices. The rest of it is in pumped hydro, and even within the whole space, that's better, thank you. With the whole space, lithium-ion batteries are playing a very small part of the puzzle. Now, I think one of the things that we have to appreciate is that we're very close to reaching theoretical limits in these areas. So we need to think about new ways of storing and converting energy. And if you look at the lithium-ion battery, it was developed 25 years ago, and in that time, its capacity has gone up by a factor of about 3 from the original lithium cobalt oxide systems to the NMCs, largely by some materials engineering, a few new materials, and also just a lot of very good engineering. Its cost has come down by a factor of 10, and Tesla and other companies have projected that it will go down by another factor of almost 3 by 2020. But I think you have to appreciate that this increase in energy density comes with safety consequences. And some of these battery incidents recently have just literally come from trying to shove more energy density in limited amount of volumes. And so I think we have to think about optimizing the systems we have, and also as scientists and academics in this space, think outside the box to radically new technologies that may not be ready for purpose in the next few years, but have future prospects as we moved forward for 2020, 2030, and 2050 targets. So just to sort of point out that the batteries are currently use 1/3 of the lithium world production, but if you look at the projections for the roll-in for electric vehicles and all of the cathode materials that are using lithium, their use is set to explode, no pun intended. And if you look at every single projection of how fast electric vehicles would roll out, they all underestimated that. And what about, is there enough lithium? Well, I would argue there is. Some might argue it's where it is in the world. In my personal opinion, it's not so much about the lithium, it's about the other elements like cobalt. And ultimately, if you're going to make a battery the size of this room out of lithium, you're going to have to recycle. So what are we trying to do to improve energy density in this space? So there's a lot of work on pushing the limits of current technology, so improving the layered materials that we have on the cathode. And on the anode, a lot of work has been going into trying to replace the graphites in our standard batteries with silicon. And the reason we do that is that you can get an almost 10-fold increase in capacity by reacting lithium with silicon. Almost 4 lithiums reacting with 1 silicon atom, as opposed to 1 lithium reacting with 6 carbons. The challenge with silicon is that it comes with a massive volume expansion, essentially associated with the size of lithium metal. And so it doesn't form a stable passivating layer, and I'll come back to that more later, and so you get continued reactions. And so at the moment, the sort of strategy in the industrial side is to combine silicon with some carbon to get a little bit of increase in capacity, but not put all of your eggs into the silicon basket, which still has longevity issues. So then we can think about moving to beyond conventional lithium-ion. So trying to use cheaper, more sustainable materials. And there are obvious candidates like lithium-sulfur. One of the challenges of lithium-sulfur is that it reacts with lithium plus sulfur to form Li2S, and the sulfides that are formed in between go into the electrolyte and end up on the other side and decompose, and so there are issues there. The sort of ultimate battery is the so-called lithium-air battery, where lithium reacts with oxygen to form peroxide. And why it's the ultimate battery is that it has the energy density of gasoline, both theoretically and practically. And so if you could get that to work, it would be transformational. The challenge is that it has all of the problems of a battery and all of the problems of a fuel cell, because you take oxygen and you put it in reactive a porous electrode to make a solid material. And I'll touch on that later. And then we can think about moving beyond lithium to other elements such as sodium. One of the nice things about sodium is that you can use a much higher abundant element, but also you can replace the copper current collector by aluminium. So unlike, clearly when I move into the picture I get there, and then I move out, it gets a big screen. Oh. Whatever. So if you put an aluminium current collector with lithium, you form a lithium aluminide, which you don't form with sodium. So that's another reason for reducing cost. There's, of course, magnesium batteries and calcium batteries. They're not without challenges, but they represent interesting areas to go because of the abundance of these elements. And then the ultimate in safety is to get rid of your liquid electrolyte, put it in a ceramic. But for those of you who are ceramicists in the audience or solid-state chemists, you can see the challenge of moving lithiums across a dense structure where materials are expanding and contracting all the way. But of interest for the carbon people in the audience, you can see in here that this picture where you've got the black components and white components, in there is carbon. And it's that sort of wiring where the carbons and the graphenes sort of play a role. And finally, just for sort of to complete the story, if you really want to get big, think about moving away from a concept of a box, have the box that does the electrochemistry, and then store your oxidized and your reduced elements in different vats. And that's what a redox flow battery does. And personally, I think this is truly one of the ways we have to go if we really want to sort of, again, no pun intended, think outside the box. So what about carbons and graphenes and energy storage? I just wanted to reflect for a few moments as to where graphenes and carbons play an important role. So the sort of most obvious region is in electrode material. So those are the materials where the action happens. And so as I'll show you later, graphene has a role to play in lithium-air. You can think about encompassing the lithium-sulfur molecules inside carbon structures and also make new electrode structures for redox flow batteries. In sodium-ion batteries and lithium-ion batteries, again, graphite, graphenes, and hard carbons play a role. And what I want to show you in this talk is how we use NMR spectroscopy to understand hard carbons, increasing conductivity via better wiring, and also maintaining integrity of electrodes, flexible batteries, and also for coating materials like silicon in your battery. And finally, supercapacitors, where porous carbons are critical to these applications. And then one can think about current collectors. So one thing that's done in a supercapacitor to increase rate is you have an aluminium current collector, you put carbon on it, and that helps the contact with the carbon porous structures to increase rate and also possibly help corrosion. So what I want to do in this talk, in this rapidly diminishing time, is to show you how we've developed a number of different approaches to understand carbons and how they function in these applications. And so I would argue that characterization, where possible, should be done in situ or operando, which means you study the material in its form that's as close as possible to the real thing. And so in our sodium NMR and our lithium NMR, we've developed these little plastic bag batteries that we can sit inside on our NMR spectrometer. We connect the leads to the battery cyclers, and we can watch what's going on in real time. It's an extremely efficient way of doing it because you don't have to pull the battery apart for each measurement. You can look at structures that would not survive disassembly. It's a disadvantage sometimes because the batteries themselves are often bespoke. They're made specially, which means they may not act like a real battery in some cases, but also the resolution associated with having a static battery may limit the technique that you're trying to do. But if you can answer mechanistic questions, then I think the method is worth it. So I just wanted to show you where we were in this in terms of method development. What we have are probes. So this is a probe that goes inside an NMR spectrometer, and inside there we put a little battery. It's not so simple as just taking a normal AA battery or an 18650 cell for cars, because the RF that you use to excite the NMR cannot get through the metal can. So we have to make these so-called plastic bag batteries. We attach them up to the cycler, and we attach them up to the NMR spectrometer, and we do things in automatic mode. And this just shows you another little picture of the batteries. This is a new development of battery systems. These are special batteries that have better pressure on them, which is useful for particularly looking at difficult materials to analyze, and also ones that are particularly moisture sensitive, like the sodium carbon systems. And so we've now used the method to look at a whole variety of different systems, be they methods to look at dynamics of lithium and sodium, supercapacitors, dendrites, and amorphous structures. And I'm going to start by illustrating our work in supercapacitors. So supercapacitors find use in applications where rapid responses are needed, and so they're sitting in your mobile phone, and they're what allows you to take a flash. So you get rapid, high-power application there. And this is nicely illustrated in a so-called Rigoni plot that plots the power versus the energy density. So if you want a high energy density material, you go for a battery. If you want a really high power application, you go for a dielectric capacitor. If you want something in between, you go for an electrochemical device, electrochemical capacitor or a supercapacitor. And they're very simple to think about how they work. All you do is you take a porous carbon, you put it in a salt solution, and when you charge, you store charge by forming a double layer of the charged carbon with the opposite charged anion or cation. And they're already finding use in places in transport where you can get rapid charging between stops. They're in the emergency exits of the Airbus, and they're also in these cranes where you're converting potential energy very quickly into electrochemical energy. There are a whole variety of different carbons that are used with different costs associated with them and different applications, including graphene sitting here with moderate volumetric capacities. And so far, the cheapest and the ones of highest volumetric capacities are the activated carbons, and these are largely the carbons that you would have in your water filtration systems. We're going to use electrolytes of different sorts. The standard electrolyte in the past has been one in acetonitrile, where you have an anion BF4- and a cation ethyl NET4 molecule, so nitrogen with ethylenes there that's positively charged. As we move forward, there's a lot of work to push towards ionic liquids, because that allows the voltage range to increase. And then if you're interested in cost, then you would use an aqueous system, but then you reduce the voltage window. So what do these carbons look like? So you basically take a coconut, you steam it and activate it, and you make these beautiful hierarchical structures where you can see the holes that have come from the original lignins of the materials and also from the bubbles as you activate these systems. And they have very, very high surface areas. So I want to analyze a bit why they have the surface areas they do. So this just shows what the pores look like. This is a beautiful tomography image taken by Paul Shearing and his team, just showing you the original structures that come from the original biomaterial and just showing how hierarchical they are. So what does the local structure look like? So this is sort of a cartoon of these hard carbons. They're largely these curved graphene structures. And the question is, can we do better than that in defining a structure? So these are two commercial hard carbons, and they largely they're optimized to give pore widths that are about a nanometer. And the reason why that's important is that's about the size of a solvated ion or cation, so you optimize the storage of the anions inside and cations inside the pores. So what does a diffraction pattern of one of these look like? So in blue is a typical diffraction pattern of a graphite, and down below is a hard carbon, and you can see there's no long-range order, but there's still nonetheless weak intensity from the total scattering or the diffuse scattering, which indicates there must be short to medium long-range ordering. And so what we've done over the last few years is to use a technique called paired distribution function analysis, where you can take the total scattering pattern collected in a synchrotron source or in a neutron source. We do a Fourier transform, and we convert reciprocal space into real space, and then you get a series of correlations that tell you something about the local structure. And so for a carbon, the first peak you get here is the carbon-carbon bond, the second one is the cross, a ring, and so on. And if you analyze this in more detail, the width of the peak tells you the distribution of carbon-carbon distances, so it tells you something about the local disorder. The intensity of the peak tells you how many carbon-carbon bonds you have, so it tells you something about the coordination number. And then the gradual, or this decay of the system tells you about the coherence length, so the degree and length scale of ordering in these materials. And so if you just compare a typical porous carbon with simulations of graphene and graphite, you can see that the correlations are very, very similar, but you're missing the correlations that would come from the stackings of the carbon sheets. And so these systems are largely based on curved graphene sheets. And each of these wiggles are real, these are not noise, and they tell you about the nature of the structure. So what about the NMR of these types of systems? So this is an NMR spectrum now. We're going to use boron to characterize BF4-. And if you look now, we have an electrode film, and we're gradually titrating in increasing amounts of the anion. And so at low concentrations, you get a peak here, which we assign to ions absorbed in the nanopores. As you increase in intensity, a second peak comes up, and this is the ions in the macropores between the particles, and at high amounts of solvent, then you get the free ions. And so can we prove that? We can prove that, and this is a collaboration of Yuri Gogotsky and Drexel, where he took some of his carbide-derived carbons and C13 enriched them, and then we can do a transfer magnetization from the C13 to the protons, and we only see the confined molecules or ions inside the pores, and we can clearly see a signature of the TAA plus cations. So where do the shifts come from? It turns out the shifts are not due to the chemical environment, they're due to a susceptibility effect. And they come from the fact that these ions are sitting on top of these large graphene sheets that are highly aromatic. And for those of you who remember your organic chemistry, you'll remember that benzenes have ring current effects that dramatically affect the proton NMR of a benzene molecule. And in the same way, if you're a molecule that sits on top of a benzene ring or a graphene sheet, you get a shift due to this effect. And what's interesting, if you look at the fluorine NMR, you get the same shift. If you look at the proton NMR and the boron NMR, it's all the same. And so we can calculate this via so-called nuclear-independent chemical shift calculations. And what we do is we take an anion and we move it closer to increasingly large fragments of carbons, from coronenes to circumcoronenes to dicircumcoronenes. And as we move closer to the surface, we get a bigger shift that depends on the size of the graphene fragment. So we understand where these shifts come from. We can now look at this inside our material. So now what we're doing is we're making a supercap, and we're putting the supercap now inside the NMR spectrometer, and we're going to charge the supercapacitor positively. And so what you're seeing now is the positive electrode and the change in the fluorine signal of the BF4- as you go from 0 volts up to positive volts. And so the most apparent thing that you see is a shift of the peak that I told you was inside the pores. And what you're watching is, interestingly enough, the change in the local environment of this signature. And so the question is, I told you before it was aromatic. What's happening now? Well, what's actually happening is that you're pumping holes into the carbon, or you're pumping electrons into the carbon, and the carbons are becoming less aromatic. And so you shift to the right because you're aromatic, and you shift to the left, as these calculations show, because you're anti-aromatic. So we're actually probing the density of states in these carbon structures directly. This is now an MRI experiment where we can look at both the negative ions and the positive ions directly in collaboration with Alexei Jershai and NYU. And what you can see now is the positive ions and the negative ions are both moving backwards and forwards as you're putting in holes or you're putting electrons into the system. So how does charging mechanisms occur? So before we started, there was an idea that you actually didn't have any ions inside the pores. You only got ions inside the pores when you charged them up. Our NMR showed that even at 0 voltages, there were equal numbers of cations and anions inside the pores. You can then, when you charge something positively, recognize 3 limits of mechanisms. You could either kick out positive ions to maintain charge balance, you could absorb negative ions, or you could swap them around. And because we can do NMR spectroscopy in both the cation and the anion, we can actually separate between all of these mechanisms. And so this is a plot where we're charging positively, and we're looking at the cations and the anions. And what you can see, interestingly enough, when you charge the positive voltage is you get an ion exchange mechanism. The positive ions come out, the negative ions go in. But interestingly, when you charge to negative potentials, the anion concentrations stay about the same, and all you get is cation adsorption. So there are 2 mechanisms that go on in these systems. And then, and this is now in collaboration with Patrice Simon's group, using electrochemical quartz crystal microbalance measurements, we can measure the mass changes on charging, and what we can then do is calculate how many ions go in and how many solvent molecules go in at the same time, and we were able to show that you only get partial desolvation of these molecules. So what are the implications of these mechanisms for charging? Well, what to do and to look at that, what we did was to measure how fast the ions move inside these pores, and we can do this with the so-called pulse field gradient measurement. And what you do is you put a gradient across a system and you measure the decay of the NMR signal as a function of time. And the longer you wait, you can distinguish between ions that are constrained because of pores, and the ions can move in free environments. And so this is now a plot of the solvent. So this is the diffusivity for the solvent versus the confined system. And you can see there's a decrease in the transport by 2 to 3 orders of magnitude between the anions and cations in a neat solvent and inside the pores. So that's not too surprising. What is interesting, though, is we can actually measure transport as a function of state of charge. And what you're looking at here now is the diffusivity of the cations and the anions as you go to positive voltage and you go to negative voltage. And if you remember, I told you in the last few slides that when you go to positive voltages, you swap ions, so the number of ions in the pores stays constant. And what's interesting is the diffusivity stays almost the same. Whereas when you go to negative voltages, when you shove more ions inside the pores, everything's more crowded and the diffusivity goes down. So pore stuffing reduces diffusion. So we now have insights which we can now use to try and design capacitors of higher rates, because this is ultimately what you do not want if you want a high-rate capacitor. So I'm going to change gears now and now move to sodium-ion batteries. And the reason I'm going to tell you about this story is that sodium-ion batteries cannot use the standard graphites that you would use in lithium-ion, because sodium can't intercalate into a graphite. So interestingly, lithium can and potassium can't, but sodium is just the wrong size. And so what you have to use are these amorphous structures called hard carbons. And so these have been discovered many years ago, and particularly by Mark Duff and others, and a lot of work has been done to try and understand how these systems charge. And so there are two processes. There's a sloping process. This is a plot of voltage versus a capacity, and then there's a long tail out at very low voltages. And there are two mechanisms that people have proposed. Primarily, the group of Jeff Dahn in very early studies proposed that the sloping voltage was due to intercalation, and the plateau region is due to pore filling, so sodium going in between the carbon particles. And then more recent work by Yamada's group has also said that defects are important, and that the sloping region is more to do with storage at defect sites, and the plateau is intercalation. So how can we study this? So let's go back to our PDF method. Remember, we're taking a Fourier transform of the diffraction or total scattering. And now what I want to do is to show you how we can model these data. So this in black is the experimental data, and in red is shown a model of the data against a normal graphite model. And you can see that the first two peaks might be well fit, but the long-range structural data is terrible, and so the difference is shown in green. So if we then say, let's think about the sizes of the coherence length, so let's make a 20 angstrom graphene particle, you can see that we get the coherence length well modeled, but we still have a terrible fit. So then let's think about increasing the spacing. We get some improvement to the fit, but it's still not very good. Then if we start to say, let's increase the thermal parameters in the C direction, so what we're doing now is we're basically creating disorder in the stackings of the layers, you can see that actually now that's a pretty good model for what's going on, but actually it's good here, but out there's clearly some structural ordering that we're not capturing. And it turns out that the way we can actually model these structures is to look at curved surfaces. And so we can fit the data with one model in short distances, and then at a long distance, we can actually do it via curved material. And so what these measurements are telling us is that you have curved carbon or graphene sheets, and we could even extract the radius or average radius of curvature of these systems. So lithium NMR was done on hard carbons many years ago, and this was the sort of pioneering work in In-situ NMR that we were very much inspired by. And what you see is the lithium NMR spectrum of here. This is the lithium metal. And then when you discharge, you see very little changes in the sloping region, and then you see this large shift out to about 100 ppm. And that shift is due to the night shift, which tells you that the lithium is seeing a metallic environment. And what was interesting was in the initial NMR studies of these materials that were done ex situ, In the sodium form, they didn't see any of this large shifted peak, and so they proposed the mechanism was very different. So we repeated this, and when we did it in situ, we were able to get rid of the problems due to the moisture sensitivity and air sensitivity, and you can really see very beautifully these large shifts going backwards and forwards in this sloping region. So the mechanism for lithium intercalation and sodium intercalation in a hard carbon is very similar. We then were able to analyze the beginnings in the sloping region. So this is now showing you enlargements, different technique called magic angle spinning, where you can see that in the sloping region we have a peak that's slightly negatively shifted. This is very reminiscent of what I just showed you for the supercapacitors, and it tells you that the sodium is not going into a delocalized metallic environment, and is very much consistent with electrons being trapped near defects and not being delocalized in the graphene sheets. And so we can put this all together now. This is now the PDF of the sodium in the fully as a function of state of discharge. And when we're at 5 millivolts, we can see correlations, not beautiful, that are reminiscent of sodium metal. So this is the 300, 180, and 5 millivolts, and this is the difference between the pristine and the low voltage, and you can see at least correlations that say something about little sodium clusters in the system. So we can put this together. A mechanism with a house of cards that was proposed earlier is too simple. Instead, we have these graphene sheets with coherence lengths of about 20 angstroms. They're curved. And then the first thing that happens when you intercalate sodium is that you get a diamagnetic environment, and that tells you that the electrons must be pinned near these defects. You then start to, as you go down into the sloping region, see metallic sodium, and that's when the electrons are delocalized into the carbon sheets. So where are we going next? I'm working with my colleagues Gabor Czerny and Volker Deringer and Stephen Elliott to try and use machine learning approaches to develop structures of new carbons. And what we do is we train the DFT, we derive DFT structures or smaller fragments, and then we train it to generate new interatomic potentials, which allow us to get very large carbon structures. And the reason we do this is we can then capture various parameters that we can measure experimentally, and the specific experimental parameter that I'm interested in is the sodium NMR shift, to try and correlate our NMR spectroscopy with the types of carbon fragments, and particularly the types of defects that form in these systems. So I want to end now by telling you a little bit of work about our work on lithium-air, which is, as I said before, is the battery with the ultimate capacity, but it has many challenges. So just to remind you of what a lithium-air battery is, you have a lithium metal anode, you have an electrolyte, and you have a porous carbon structure, and the lithium can react with the oxygen that's coming in through the gas phase to form a superoxide. This superoxide ion then disproportionates to form lithium peroxide and more oxygen. And then on discharge, the lithium peroxide is then oxidized to back to oxygen, which is then released, and the lithiums go back to the lithium metal anode. And so these little these reactions here illustrate some of the challenges of the system. The first challenge of the system is that the intermediate between lithium and lithium peroxide is a superoxide. And so superoxide is an extremely aggressive radical, and it basically eats up any electrolyte it sees. And so there are tremendous problems of degradation of the superoxide radicals with the electrolyte. And so the carbonate electrolytes that people use in standard lithium-ion batteries are not appropriate for the systems. And then the second problem is that you form this solid product of lithium peroxide, and it's very difficult to then get rid of this on charge because it's essentially an insulator. So you've got to get the electrons to the peroxide so as to oxidize it. But because both lithium and oxygen are incredibly light, if you can get it to work, it has 10 times the theoretical energy density of it. In practice, it's the overall practical energy densities or capacities are low because you get pore clogging, so the pores fill up with these big particles and you can't get the oxygens through. You have low rates because of the difficulties of getting the lithiums and the electrons to the peroxides on charge and getting enough oxygen into the systems on discharge. And then you get very large overpotentials because of the difficulties of doing these reactions, which results in very low energy density. Parasitic reactions, short life cycles, and also lithium metal dendrites that implicit to lithium metal technology are a problem that still need to be solved. So the other thing to point out, we always talk about a lithium-air battery, but in practice at the moment it's a lithium-oxygen battery, and that's because most of the other molecules in air, nitrogen, carbon dioxide, and water all react with lithium metal. And so we perform all our reactions in closed systems where we only have oxygen. And it's sort of incredibly irritating that even nitrogen reacts with lithium metal to form lithium nitrides. So just to sort of reflect a little bit on some of the problems of the superoxide intermediates, one of the main mechanisms you have is that you react the lithium with the oxygen to form the lithium superoxide, which then disproportionates. Now remember, this reaction is coming from, or is mediated by electrons coming from the electrode structures, and so because of that, the peroxide ions, which are largely insoluble in most electrolytes, precipitate out, disproportionate, and you very rapidly form these surfaces that are passivated by lithium peroxide, which is an insulator. And so you prevent the reaction from going on. And so you also, again, get these parasitic reactions because of the highly aggressive nature of the superoxide. And so the strategies that people are taking are to use very high donor number solvents that increase the solvation of the superoxides and the peroxides. And then you can transform this from being a surface reaction to a solution-based reaction, and you can form the beautiful large particles that I'll show you in a minute of lithium peroxide on the carbon structures. You can also use redox mediators to mitigate this reaction, and again, I'll show you that in the next slide. But the problem with the solution mechanisms is that you can get poor clogging because you form these massive particles which then block the transport of oxygen through the pores of your carbon electrodes and also block the transport of lithium ions. And this is a SEM picture of an electrode formed by a carbon called Super P, which is about 100 nanometer spherical ball particles, and you form an electrode by putting a binder together to hold everything together, and you can see that there are pores about the same size as the carbon particles that are about 100 to 200 nanometers, and then you form these massive micron-sized toroidal structures due to lithium peroxide on them, and so you can easily see how that becomes blocked. And so one of the strategies that we've been looking at is designing graphene-based electrodes in order to reduce pore clogging. So these are the pictures now showing you the Super P particles, 100 to 200 nanometer particles. This is one with titanium carbide, which was proposed by Linda Nazar a number of years ago as a good catalytic structure for this. But again, you can see that all of these electrodes, unless you do a lot of engineering, have very small pores. But if you move to these reduced graphene oxide electrodes, you can get highly porous hierarchical structures, which in principle should allow you to increase rate in these and capacity in these systems. Okay, so graphene electrodes is one strategy and route forward. The other thing that we want to do is to try and increase the solution-based mechanism, and in order to do that, we use a redox mediator. So these were pioneered by a number of groups, notably John Owen's group on using redox mediators for discharge. Peter Bruce's group were the first to come up with a redox mediator for charge. And let me illustrate what that means. So if you remember in a fully discharged battery, so this is the discharge here, where you're plotting potential versus the capacity, what you do is you form a large lithium peroxide particle. Remember, it's an insulator, and in order to oxidize this peroxide from a peroxide ion to oxygen, I've got to get electrons into the system. You can imagine that if you just do that, the only mechanism getting an electron is at that interface between the particle and the carbon electrode. But if you have a redox mediator in there, that mediator can go in and it can be oxidized itself, so fulvalene can be oxidized, it can then go into solution, and it can go off and it can react anywhere on the surface of this particle to oxidize the lithium peroxide to oxygen. And so this is now the plot from Peter Bruce's group, where they show the discharge. So this is on charge without the mediator, and with the mediator, you can see there's a significant reduction of the overpotential between discharge and charge, which then directly relates to an increase in efficiency of the battery. So this is a charge one. For discharge, they proposed a benzoquinone, so DBBQ, which again does the same thing. The difference now is that the quinone itself gets reduced. It then finds, on the carbon electrode, it finds an oxygen molecule, and then it then can react anywhere to form these extremely large lithium peroxide particles. And so what we've been doing is to work on the effect of water and these DBBQ molecules. So water increases the donor number of the solvent, but it also, interestingly, changes the potential at which these redox mediators work. And so this is the reaction, or the CV plot, of a dry DBBQ molecule. So this is the first reaction to form the first reduced molecule. This is the second one. And when you add water, what's interesting is the potential shifts closer to the voltage of the first reaction to form the superoxide, which is what you want. So this looks more promising to add water to these systems. And so this is now a comparison of Super P and RGO electrodes, and this is the discharge capacity with no water. Then we add DBBQ, and you can see it improves significantly. If we move to a graphene electrode, we get a much better voltage versus capacity. We then add water, and you can see the capacity increases dramatically. And so you can see this more clearly if you're not an electrochemist. If you look at the SEM, here are the two electrodes. In the absence of water and DBBQ, what you can see is the electrodes very quickly get passivated by the lithium peroxide, so the reaction shuts off because you have no more mechanism of getting electrons into the system and reducing the oxygen. You put DBBQ in, and then you can start to promote these solution-based mechanisms, and you can see much bigger particles emerging. And then you put in water, and you get these monstrous particles that are sort of more than 10 microns in size, and you get these beautiful toroidal structures and a significant increase in capacity. And what's interesting is that if you look at these electrodes, you can still see bare parts of the carbon surfaces, and the capacity is actually not limited in this case by the volume of the electrode. Okay, that's telling me death, like my batteries. So you could actually go further if you had more lithium source. So we're actually limited by how much lithium we had on the anode of our materials. And so the only thing I wanted to say was that redox mediators can also change the chemistry. This is our work previously looking at triiodide reactions. So you can use iodides as redox mediators. Iodides going backwards before was between iodide and triiodide, and they are sitting at very much the same voltage as the lithium, the oxygen reaction. And so the only thing I wanted to point out in this system, that instead of forming lithium peroxide, we actually change the chemistry and we form lithium peroxide. And we form these monstrous, again, particles of lithium peroxide. We can actually do this reversibly. And what's interesting is because we form a hydroxide, not a peroxide, we get dramatically reduced amounts of degradation products. And we can see the degradation products in the proton NMR confirming this. This is a more clearer spectrum. So this is the the hydroxide that's formed with water. If we remove the lithium iodide, you can see instead of forming hydroxides, we form peroxides, but we also get significant decomposition products. We can follow the mechanisms of where the hydroxide's coming from by doing oxygen NMR. So we prove that the oxygen comes from both water and oxygen via this oxygen NMR signal. And we can track whether this is a 2-electron mechanism or 4-electron mechanism by doing these pressure cells. And so with that, I will not tell you about our experiments on, unless I have 8 minutes here. That's fine. So we've used graphene experiments to look at passivating layers on carbons, specifically the SCI, which is a very effective mechanism or way of looking at these decomposition reactions, and that's a story in itself. So I'd like to end by saying I hope I've shown you that graphene can be used both as a platform to understand electron decomposition mechanisms, which I just rushed over very quickly, but more importantly, that by using these NMR techniques in combination with other techniques like pair distribution function analysis, we can really get very detailed mechanisms about how these diverse forms of carbons store charge. And finally, I ended up by telling you that we could get very high capacity graphene electrodes, and we could get very high capacity batteries by using these graphene electrodes. I should just acknowledge a few people who've been involved in the work, particularly the work of Alex Force and John Griffin, and Hao Wang, who worked on the Supercap project, Ollie, who worked on the robot and the in-situ methodology. The Lithium-air work has really been pioneered by Tao Liu in my group, along with Gunwoo Kim and Wenjin Yu. Sodium anodes is the work of Josh Stratford and Phoebe Allen. I've had wonderful collaborators, funding from the Cambridge Graphene Center and the Flagship, significant large interactions of Andrea and his team on the graphenes, Supercaps with Patrice Simon and Yuri Yagotsky, and thank you very much for listening to me.
So thank you very much, Claire, for this beautiful overview. Now the floor is open for your comments, questions.
Thanks very much. Beautiful talk. You showed a lot of insight into the mechanism of the ions entering in graphite and in these carbon materials. Another important part is the solid electrolyte interface. My question is, what's the status on this important interface in the field, and can nanomaterials also help to control and improve this important part of the battery?
So sadly, I didn't spend very much time talking about that. I mean, my feeling is that the SCI, so for those in the field who are not in the field rather, at low voltages, you will react, the electrolyte will react, it will decompose, and so you have to minimize the surface areas of your structures at low voltages. You can reduce SCI formation by adding additives, as you know, like FEC and VC, but ultimately, I think the role that the carbons play is possibly in stabilizing the surfaces. And so the problem with silicon is that it expands and contracts, and so it's always exposing fresh surfaces. So I think that these carbons will play a role in trying to create more stable structures. But one thing that's sort of the bad news in the field is people are adding silicon with graphites, and these expansions of the silicons are actually grinding the graphites. So that's going to be another problem we're going to have to address, because you've got this particle that's, it's not as soft as I used to think it was, it's expanding threefold, and it's pushing all the carbons nearby. So it's a real challenge to sort of to solve those problems. So I don't have the answers to that one, I must admit, I've been trying to work on this for 10 years now. So, but I have clues, but not answers.
Okay, thanks.
All right, any other questions? Or comments? Or contribution? I didn't see, oh, over there, sorry.
Thanks for this very interesting presentation. In the end, you mentioned that water as an additive is actually helpful for a lithium-air battery. And before that, you mentioned the present stage that the battery needs to be protected from anything but oxygen. So is this water as an additive something you could think of coming in from air moisture in the end, or is it orders of magnitude too much what air would offer?
Well, I mean, that was sort of another reason we were doing that, is that you can then tolerate some water. The problem you have, of course, is the lithium metal, that we've been very successful in getting multiple cycles because you form a hydroxide on the lithium metal that passivates it to a degree, but is that enough for it to be commercial? But the sort of field is moving to protecting the lithium metal with ceramic, which will also help you against the nitrogen problem. So if you can get the lithium metal solved, the big if, which will be useful for so many other fields, then you could probably deal with more water. But I think you're still going to have to control the water. So you're going to have to because you can't have infinite amounts of water into the systems, unless your lithium metal is protected properly. But I think controlling water is a much easier one than actually doing the oxygen-nitrogen separation. So I'm less worried about that. I think you can, that's a manageable problem. But I still, solving the lithium metal problem is still a challenge. I think we can deal with a little bit of water in the systems and cycle in a lab scale. Whether you can scale it up for a commercial system is quite another matter. Because lithium hydroxide is quite an important component of the SCI, which is why you get away with it.
More questions? Help me see any hand raising, because I don't see. Well, I guess that if there's no any other comment or question, we can again thank Clare for her contribution. And now it's the time for